Okay, we're trying something a little bit different here. Um, we're going to be talking about limits. Jeez, I can't even spell here. Limits. And so the question is, what in the world is a limit? And so the idea is for a limit is that we have some function, right? And that function, the the function uh, does. Well, what does the function do? It ties values of the domain to values of the range, right? So it ties values of x to values of y. Okay, therefore, if x changes, that induces a change in y. Right, so just as a quick example here, here's a function f of x. Um, now f of x is, how does f of x tie the domain to the range? For example, here at this point, if I'm looking at this domain point, then the function ties this point of the domain to this point of the range, right? So this point on the x-axis is tied to this point on the y. Okay, so now if I move this point over, what happens to the point on the y-axis? Well, initially we can see that as I move my x-axis, or as I move my x value over, my corresponding y's are going to start to decrease for a while, right? And then at some point they're going to reach a smallest value. So my y values are going down and down as my x values are coming across. Can you see that? And then what's happening if we continue to go across, then the y values are going to start increasing again, right? To about here. And then they'll start decreasing again. So as x moves from the right to the left, right? It's coming, we could say it's approaching 0 if you like, from the right-hand side. Then my y values are initially moving down and then moving up, and then they move down again, okay? And so kind of the game we're going to be playing in this section is we're going to be moving x in a particular way, and we want to answer, well, what happens to y? Okay, so let's try an example. Maybe I'll just go ahead and show you the example in the book for the first part, because there's a nice numerical table as well. And so the question here is, we want to find out, this is my function right here, x squared minus x plus 2, which is graphed here. We want to find out what happens as x approaches 2. And so you can see here on the table that initially my x is starting at 1 here and then working its way to 2. Geometrically, where are we? Geometrically, these are the values of x right here, right? So we're starting at 1 and working our way to 2. And so the y values we can see are being computed here for us, which is kind of nice. So we start at 2, so 1, 2 is here. And then, so that's 2 on that y-axis. And then we go closer to 2, 1.5, then 1.8, 1.9, 1.99, 1.99999. Okay, and you can kind of track the y values to see what they're doing. And if we track the y values, it looks like they are approaching maybe some number. So for example, if I were to get even closer to 2, like 1.99999, what would you expect to be here? Probably something like 3.99999. Okay, so what we see here then is we predict that the y values will be going to 4 as x approaches 1, or sorry, as x approaches 2 from the left. Okay, now what happens as x approaches 2 from the other side, which is the right-hand side? And so as x approaches 2 from the right-hand side, we see that the y values are being computed. And what do you notice about those y values? Those y values are also coming down, decreasing, and it looks like they're approaching 4. Okay, so therefore, we would say that the limit as x approaches 2 of x squared minus x plus 2 is equal to 4. Okay, but notice that there was 2 directions of travel, right? We took x from 1 to 2, and then we took x from 3 to 2. So we took x as we approached 2 from the left, and then we looked at x when it approaches 2 from the right. And we looked to see what our y values did, and the y values were approaching the same number, 4, and so we said that the limit as x approaches 2 of f of x is equal to 4. Very good. So now let's go ahead and define what we mean by a limit. And the definition will need a little bit of explanation as we go, because there are some weird things that can happen to a function that we may not be expecting. Definition: the limit as x approaches a of f of x equals L. Well, maybe I should start off by saying let f be a function defined on an open interval. I'm going to explain what that means here in a sec. Open interval containing the point x equals a. So geometrically what that means, if this is my point A, an open interval is one that does not contain endpoints. So the endpoints are excluded. Also, in our definition, we don't care what happens at the point A, and so I'm going to put an open circle about this point. And so my domain for the function, using this definition of a limit in just a second, I'm going to want to have f of x defined in an open interval about x equals a, and I don't really care what happens at a. So I'm going to leave that open there. Good. Then this notation comes in, and how do you read this notation? This notation is read as the limit as x approaches a of f of x equals L, and that means that we can force, I suppose, the y values to be arbitrarily close to the number L. Now this L is a y value, so it's on the y-axis, right? By taking x sufficiently close to the point x equals a. So the point A, where am I? Oh, I don't have my graph. Here's my point. Here's my A. Here's my L. Whoop, L. Okay. So what we're saying is that my y values can be forced to be close to L by taking x sufficiently close to A. Good. Oops. I see that you can't really see the bottom of that page. There you go. Okay, so there's a few cases that can happen here. This is kind of a typical case where you just draw the graph right on through, but there's also a case where you might have an open circle at this point. In other words, this may not be defined in your domain. It may also be the case that it is defined, but you have some kind of a, you have some kind of an open hole there, but the actual value of the function may not be at the same point. So in each of these three cases, the limit does exist and it's equal to L. Okay, so now what we're going to do is I'm going to stop here, and in the next video we're going to take a look at more examples of when the limit does exist and when the limit does not. See you then.